Good evening, and welcome to Hampshire College Lecture Series on Science and Religion. This is the second year of the series, and the theme for this year is a history of conflict and cooperation. Before we move on to the introduction of Dr. Saliba, just one announcement about our next speaker. Our next lecture will be on March 28th, which is a Friday, and Dr. George Coyne will talk about, and his title is The Dance of the Fertile Universe, Did God Do It? And again, the announcements are available on the back side. You can see the abstract for that. And as usual, we are videotaping these lectures, so you have cameras over there, and we make sure that they end up online, and you can find our previous lectures at Science and Religion, one word, scienceandreligion.hampshire.edu. We would also like to thank our sponsors, the Hampshire College Integrated Science and Humanities Initiative, Hampshire College Office of the President, Office of the Dean of Faculty, and the Schools of Cognitive Science, Natural Science, and Humanities and Cultural Science. We are extremely privileged to have Dr. George Saliba with us. He is Professor of Arabic and Islamic Science at Columbia University, and I just found out that this is his 30th year at Columbia. He works on the development of scientific ideas from the late antiquity to early modern times, with a special focus on the various planetary theories that were developed within the Islamic civilization and the impact of such theories on early European astronomy. He is a recipient of a number of awards and honors, including the History of Science Prize by the Third World Academy of Sciences in 1993, and the History of Astronomy Prize in 1996 from the Kuwait Foundation for the Advancement of Science. He's the author of several books, including the astronomical work of Mu'adh-ud-Din al-Urdi, a 13th century reform of Ptolemaic astronomy, A History of Arabic Astronomy, Planetary Theories During the Golden Age of Islam, and his most recent, that came out last year, Islamic Science and the Making of European Renaissance. I should also note that we had already scheduled Dr. Saliba last year, and then I found out that he was going to give lectures in Pakistan also. So I had an eye on it when he was going to Pakistan, and he delivered lectures over there starting from November 4th. And November 3rd was the time when Musharraf imposed the emergency. And so I was worried whether we are going to have this lecture or not, whether he'd be able to come back or not, but apparently everything went fine despite the emergency. So let's welcome Dr. George Saliba.
I think I'm going to try to turn on my mic. You can hear me in the back? You can hear me well. So we don't need this guy anymore, but if I move away, you can still hear me? So my mic is working? All right, so we are in business. Thank you so much. Thank you, Salman. Thank you for coming in such a beautiful day. I'm especially grateful that you decided to sacrifice the environment outside and to come here. But at the same time, I'm also touched, especially by the students that I managed to talk to them a little bit earlier, and the students that I didn't talk to. But let me start by saying what I intend to do today. As you can see from the title out there, I wanted to discuss this issue of what happens when science crosses cultural borders, especially in an environment where we seem to think that science is such a universal construction, and hence it shouldn't have any difficulties when it crosses from place to place, and it should be, and the model that most people use is that, look, 2 + 2 is always 4, it doesn't matter which culture, which language, and so on. But there are all sorts of very serious ways in which culture redirects science. And what I want to do today, I want to spend most of the time talking about what particular requirements Islamic civilization imposed upon science, that science had to come up with an answer when we know that the background science that had to come up with that was mainly Greek science. And here we are talking, again, if not folklore science, we are talking of science at the highest sophistication of mathematics, astronomy, and so on. So, to start with, what I will do, I will first disabuse you of some of the mythologies about the origins of Islamic science and the fate of Islamic science that you find them in most history books, that I think we should dismiss them very quickly. And as you will see, the brunt of the lecture will be to respond specifically to the first myth. Everybody thinks that Islamic science, what they did, they just preserved the Greek science so that Europe could pick them up and use it, and hence, thank you very much, and then they go home. This would be, if it were true, it would be the very first civilization that I know of that could have such prophetic vision that they will pick up a science that 500 years later will be useful for a second civilization. And we are not going to attribute that kind of prophetic vision to Islamic civilization. More concretely, I will show you that in fact there was a whole lot of debate with the Greek science, and in great number of cases a refutation of the Greek science and the whole remodeling of Greek science, that by the time it comes to Europe it can be literally called Islamic science, and I will tell you why. Here again I will use the terms Islamic and Arabic sometimes interchangeably, simply because most of the science, you can hear me still even when I move around, most of the science that was written in Islamic civilization was written in Arabic. So I don't mean to use the term in any ethnic significance whatsoever, especially in a civilization that says there is no virtue for one race against another race except by the measurement of their piety. This is the very brunt of Islamic civilization. So hence, to talk of Arab, Persian, Turkish is not in the spirit of Islamic civilization. Two, I will also use them with an ik at the end. I will use Arabic and Islamic to simply mean them as civilizational terms and not to be particularly related to religious terminology, although in some instances, as we will see today, religion had a lot to do with it, but it had it as part of that civilization and hence its requirement. Now, the second myth that I also would like to dispel, and I would like to demonstrate to you that it is indeed not true that science is always in conflict with religion, despite the fact that we do have very famous cases. Of course, the famous case of Galileo still stands on our mind, and I would like to say that that case is not transferable, it's not universal. In other words, if one culture happens at one point to actually manage to confront science, meaning religion, confronting science in that culture, that does not make it a universal principle, and hence we should expect all other cultures to do the same. As you will see today, and I hope that I'll be able to demonstrate it, that in certain instances religion can itself instigate all sorts of scientific research that will become very, very useful later on, not necessarily to always solve religious problems. Things may start at the beginning to solve a religious problem, but once they become a tool, then you will be able to use it all over the place, and I will show you how this took place. The last myth that I would like to also dispense with is that most people think that the transmission of Arabic science to Europe happened during the Middle Ages, and simply because we have already known a lot about the translations from Arabic into Latin during the 13th century, up to the 13th century. And there are some brilliant books written on the subject, but very, very little is done on what happened after the 13th century. I will show you that the transmission continued to go on well into the 16th century and at levels that are considerably more sophisticated than the levels that took place in the early period. Now, to start with, I will start with two examples from where a simple religious requirement necessitates very serious scientific research. The first requirement comes from a reading of a verse from the Quran. I will read it in Arabic, you can read it in English, which simply says, أَقِمِ الصَّلَاةَ لِدُلُوكِ الشَّمْسِ إِلَى غَسَقِ اللَّيْلِ وَقُرْآنَ الْفَجْرِ إِنَّ قُرْآنَ الْفَجْرِ كَانَ مَشْهُودًا. A simple statement that says, pray, in effect. That's what it says. And if you are a Muslim, you know that you have to pray 5 times a day, and now the complexity begins to come in. when do you pray? The definition of the prayer time in Islam immediately becomes an astronomical problem, and I will tell you, show you why. As you see on the screen, you have the times of prayers are marked, and I think I brought my own pointer. Bingo, we have it. So Islamic times, very, very rarely, by the way, Islamic prayers, very, very rarely happen at a punctured time, meaning like you don't hear the bell and immediately fall down to pray. No, you have a little bit of a leeway so that you don't think that prayer is such an what do you call it? Such a pressing need. You have a time to begin it, you have a time to end it, so in between those two limits you can pray. The very first prayer is to pray between dawn and sunrise. So you have that. Of course it becomes a problem. When does dawn begin? When is it that is dawn? And the traditional Islamic explanation was to say it begins as soon as you can tell the difference between a white thread and a black thread. If you can see that there is a difference between them, that's the beginning of dawn. And that is a good rule of thumb you'll be able to do to determine. Second, across from it there is another prayer, which is the twilight prayer, the Isha prayer, which is also after the sunset, but before night sets in. Also, you use the same rule of thumb, and you'll be able to do it. Now, astronomers are never satisfied with the rule of thumb. Of course, they want to give you precise answers, and the precise answer that you get from the astronomers is that dawn begins when the sun is still 18 degrees below the horizon. And they use that to be able to compute from that number, they be able to compute the height of the atmosphere, because they knew that it is the sun's rays that are reflected through the atmosphere, and so on. So you can immediately see that the very simple requirement to pray at dawn led you immediately to very complicated computations of the height of the atmosphere. And if I had time, I published an article on this quite some time ago in 1984 or so. I could devote another lecture to that. But immediately you begin to see that simple religious requirements are not as simple as you think they are. The next prayer that you have to perform is what is called the noon prayer, and that also is not to happen at the time when the sun is exactly on the meridian, because it may look, or at least I think the early interpretation was, it may look that you may become a sun worshipper if you are really praying at the time when the sun is at the horizon or sun is over. If you define it that much by the body of the sun, they didn't. And Islam is very, very, I would say, very allergic to the idea of idolatry, that they want to move as far away from any interpretation that could possibly mean adulterous behavior. So what the definition is that as soon as the sun begins to lean towards the west, that is the time to have the noon prayer. Or again, with the rule of thumb, as soon as you begin to see the shadow of the diverting or moving in the western direction, eastern direction, then you pray. The most critical time to pray is the time of the Asr, i.e. the afternoon prayer, and that caused a lot of problems. Why? Because it is in between times. It is a time during the day. It's afternoon, but it is before sunset. So what is a good time to pray during that period? And the first rule of thumb that was used when the community was still down in Mecca was to say that you can pray from the time when your shadow is equal to your height. See that right in here, the shadow is equal to this height, in this instance, I think, to the time when the shadow is twice your height. That is a good rule of thumb. Except that the minute you move north of Medina, and you can test it for yourself right here in this city, by the way, in this area here, in the winter time, as we are still really going through winter time right now, there will be times when your shadow is never equal to your height. It's always much longer than your height. So what do you do with this situation? You stop praying? No. Of course, the astronomers came in handy at that time, and they said, oh, what we need to do is to define whatever length the shadow had at noon, and add to it either your length or twice your length. So in other words, take a fixed shadow that is at noon shadow for whatever geographical locality. But that immediately opened doors. It says that if you moved from Mecca to Medina, you go to Damascus, those requirements are changing. Therefore, mathematical geography and where you are on the globe has significance. Therefore, we have to compute length of shadows for every single degree of latitude, and they did that. To such an extent that a famous astronomer by the name of Biruni computed them to every single latitude until he reached 44, which is about New York latitude. He said, from here on, there is no more civilization. We don't need to worry about it. But you could see the urgency that they really felt. Every time there is a little problem that opens, they go at it and they try to solve it in general, as much as you can extend with it. So the serious problem of the Asr player, of course, led to the definition of what is the length of the shadow at noon for any locality that we can go on the globe, and hence now regularize mathematical geography, regularize the shadow so that we can add our height to it and twice our height, and so on. So immediately we need to know what is the angle that the sun will cast at noon here. Let's call it the height of the sun at noon, and hence from it determine the length of the shadow. You think that this is nice, but then as soon as you look at it, that they knew, by the way, nobody had to wait for Christopher Columbus to tell them that the earth is spherical, okay? So this mythology, I don't know who started it. Even Columbus himself knew, and the Europeans at that time, if they had read their classical antiquity, right, they knew since the time of Eratosthenes that the earth is spherical, and it was even measured in the 3rd century BC. Well, so Islamic astronomers knew very, very well from the very beginning that they are playing with spherical trigonometry, that they are playing with spherical universe, and so on. So for a quick rule of thumb, they immediately determined, they know that the sun moves on the ecliptic from day to day, but every day it follows what we call a daily arc, which is marked here in blue, and the highest point the sun reaches here is really inclined from the angle of the complement of your latitude of your city, and let us call it the inclination of the sun delta here. They knew that this value changes, and it reaches sometimes a maximum value when it is here, and reaches a minimum value when it's here. But in between, we can always calculate the height of the sun as equal to the complement of the latitude of your locality plus or minus delta. So now you're already getting into mathematics. But already they knew also that the shadow that is going to be measured here is nothing but G, that is the height of the gnomon, times cotangent the height of the sun at noon. I have news for you. There is no cotangent in Greek science. There is no sine in Greek science. There is no cosine in Greek science. Hence the term tangent doesn't exist. There is the Menelaus theorem, which solves some trigonometric problems, but not as efficiently as the trigonometric problems that comes through the sine, cosine, and so on. So as the first step to solve it, you already feel that they have to create new concepts that were not known in the Greek tradition, and we will see that a lot more of those concepts were created. The problem, therefore, now is reduced to be able to determine S. You have to know the height of the sun at noon. To know the height of sun at noon, you have to know delta, because this complement of the latitude of your place is always a fixed quantity. You measure it once. But what changes from day to day is this delta. Therefore, this delta is a very useful variable, and they needed to solve it. They immediately also knew that delta is an intricate little value. Not only does it come as an inclination of the sun on its daily motion, that this is a delta, that's another delta. So from day to day, this delta changes, and itself is a function of two other variables. It is the position, where is the sun on the ecliptic, and that lambda here is the longitude of the sun, and it also depends on the angle between the ecliptic and the equator, that we call it usually the inclination of the ecliptic, and that epsilon is also a fixed quantity. You can measure it once, and that's it. From there on, you can use that epsilon. So the two variables that you have to use, the longitude, and you have to compute also this delta in order to plug it back into the function that we had before. They also found out that the Greek science does not have such a thing that we call the sign law. This sign law that is expressed in here does not exist in any other culture before the Islamic civilization, neither in Greek nor in the Indian tradition, that's in Sanskrit, where there would be the other source of mathematics that they would have got into Islam. And hence, the invention of the concept of sign law, together with the cosine law, by the way, and all of these other laws that you see them, the trigonometric identities, all of them were developed sometime between the 9th and the 10th century, mostly in a city called Samarra. Unfortunately, we hear it only now when it's being bombarded. That city was one of the most productive cities of trigonometry during the 9th century, and in the city like Baghdad and in other places. But the whole problem was, now we are still, you see, notice, to calculate delta, therefore I need a precise measurement for lambda, meaning for the longitude, and I need a fixed measurement for this epsilon by direct observation. How did they do that? They knew the determination of this epsilon, that there was a Greek technique of doing it. The Greeks had already measured that epsilon because you need it for all sorts of astronomical computations. There is no way of getting around it. You have to have a good measurement for it. But then what they did, and the Greeks had followed the same technique, is in fact to take any gnomon, stick it out of a wall that is oriented north-south, and then when the sun in the summer gets to the highest point, you can just mark this shadow right in here. And then when it is in the winter solstice, it gets to the highest point here. So you take the value in between. The Greeks had done that. You divide it by 2. The value between them is really this value of epsilon that we have. It's simple, straightforward, direct observation, except that they noticed that the bigger the instrument, the more precise the result will be. And hence they wanted an arc in here to be as large as possible. And indeed, I think there is an archaeological remain, and this is just a magnified slide so that you could see what they are after. They are really trying to compute this angle right in here by using this measurement. And the archaeological remain of an observatory that was built in the 15th century, and we have no reason to think that it was any different from the earlier observatories. This comes from the city of Samarkand in modern-day Uzbekistan. And during the time of Ulugh Beg, they wanted this arc to be as big as possible and to be as stable as possible so that you could do the measurements on a daily basis. They dug into the ground a whole arc like this and see the size of it. I wish there was a human being here when this picture was taken so that you can get the proportionality of it. It's a huge, humongous size, and actually it is much larger than this whole wall. So it's a very large instrument, and of course the larger the instrument, the more precise the measurement, and we will see where did this begin to pay off in the determination of epsilon itself. Epsilon is nothing but what we commonly tell the school children when they ask us, why is there a change of seasons? Now we are in summer, then we go to winter, then we go to fall, winter, spring. We tell them these seasons are there because the Earth axis is slanted. And we tell them that it is slanted by 23 degrees and a half. I have you know that this measurement of 23 degrees and a half was measured either in Baghdad or in Samarra between the years 800 and 835. We know exactly when it was measured because it's mentioned in a text that's written in 835. Before that, we have no mention of it. And we know also that this measurement is different from the Greek value. You see, the Greek value here is 23 degrees, 51 minutes, and 20 seconds. It's almost half a degree too much. And similarly, the Indian value is 24 degrees. Now you will say, I am fussing. I am asking about only half a degree precision. What kind of precision is this? We are playing in a field that gave meaning to the concept of astronomical numbers. You know what that means? That if you give me half a penny and you allow me to multiply it by an astronomical number like 10 to the power 20, I will be much richer than Bill Gates. Just half a penny. So a little bit, a half a degree, when we multiply it later on by large numbers for other computations, can become significantly erroneous. And as a result, this precision that was already built into it, the fact that it was an excellent measurement is that we still use this number up till today. We still use it in our textbooks, we teach it to children, and we tell them that the slant of the axis is only 23 degrees and a half, as you can see. Now that we determined epsilon by direct measurement, we know it is 23 degrees and a half, we need to determine lambda, i.e. how do you know the precise longitude of the sun on daily basis? The Greeks had done that. They had tried to determine it, and Ptolemy did this measure, and he says if we are here at the earth, all we have to do is measure, take the first observation when the sun is at the vernal equinox, meaning when it is going to be right there in about 10 days from today, a little bit more, and make the measurement when the sun reaches the solstice, and then when it reaches the autumnal equinox right in here, and then we can calculate all these arcs. Then I will be able to determine the eccentricity, hence I will determine all the particulars of the sun that moves a little bit eccentric from the earth. Whew. It's a little bit too fast. Why did Ptolemy have to do that? He noticed that in the summertime, in the spring and the summer, the sun seems to linger in the skies. First it comes overhead, and then it takes a longer time to finish from the vernal equinox through the solstice to the autumnal equinox. And the proof is also how do we arrange our calendar. It is not accidental that this poor February, it's not that he was a detestable Roman emperor, he just got 3 days short. So we only added a day for him this year just to please the poor February. Why are we shortening the days? Because we know the sun passes through the winter. When it is moving in this one, it passes rather fast. And it only lingers in the other. That's why we also compensate for that by making July and August, both of them are 31 days. So we put more days in there, which means, in effect, that the sun seems to take longer time when it is hovering over there. To Ptolemy, this meant that the sun is not moving around us. It's moving on a circle that is eccentric to us. That is, the center of the circle of the sun is here, and we are living there. Therefore, the measurement of this eccentricity is of extreme importance to determine where is the sun on day-to-day basis. The only problem with the measurement is that where is the sun, when does the sun reach the solstice, i.e. the summer solstice? When does it get exactly the maximum length of the day? Once we know that, we will call it June 21. In other words, the calendar comes after the phenomena. The phenomena is not driven by the calendar. The calendar is only to name phenomena that are out there in nature. To measure that position, what Ptolemy did, and now you can see the error in his judgment, meaning in the judgment, and Ptolemy, by the way, is the most famous Greek astronomer that ever lived. And he is I think he should be, we should have a statue for Ptolemy in every major city in all Western civilization, in all places, because he was the brain that thought all of these till the very extreme. Of course, the poor guy was doing this in 150 AD. What he did now, what you can see that there was a problem, is when you measure this, the moment of the solstice, it is as if you are determining, this is the scale against which the declination of the sun is every day. That's delta is varying every day. It reaches a maximum of 23 degrees and a half here. But you see that it reaches this for a considerable number of days. And how do we know this? You can also make this observation yourself. Now that we are coming in the direction of the summer solstice, all you have to do is just look around your house. There will be a time when the sun shines in the morning or it sets in the evening. I'm sure, I hope that you have a window somewhere in your house that you can see the edge of the window on the wall. And then you know, now, by the way, it moves very fast. Go back and observe the sun when it sets or rises, it doesn't matter. 3 days from today, you will see that edge will fall at a different point. Mark it with a pencil over there, and you will see that it will move. And you can observe the movement in 2-3 days, you can see it. But when it comes to about June 18, from June 18 to about June 23, the sun will rise and set in exactly the same spot. Why? Because you are making the measurement from this position. So all those days in between, you can't tell the difference out there. So that is a poor method. A poor method able to determine the actual moment of the solstice. So astronomers, again, between Baghdad and Samarra, they concocted this and they said, look, why are we obliged to follow Ptolemy and make the same observations that he made in the same spots? Why not observe the sun when it is moving from day to day and we can see the difference? I.e., observe in the middle of the seasons rather than the beginnings and ends of seasons. In the middle, they can see that the sun from day to day, as you can see it yourself too, by the way, that edge will move from day to day and you'll be able to mark it. And here again, so you can get much better precision by making the observations in different spots. Do you understand the significance? They are saying that Ptolemy is not a poor observer. He was a poor strategist. He did not choose the exact times that are most fruitful for the observation and that can give you observations that are highly critical. So we need those critical observations, and the new measurements, since they are taken in the middle of the seasons, the new method was called the method of the seasons. And hence, from there on, they could do the same measurements of Ptolemy. But notice, instead of measuring at the time of the vernal equinox, now they do the measurements in the middle of Taurus, middle of Leo, middle of Scorpio. They do exactly the same mathematics, but they just change the strategy of where you observe. And then they got immediately a better result than Ptolemy. Not only did they get a better value for the eccentricity, Ptolemy had used that method because of the poor observations, continued that line and determined here the point of the apogee of the sun. Now in one shot with the new method, they determined that the solar apogee is also now determinable here, but they found out that Ptolemy thought by his poor method that the solar apogee is fixed. He said it never moves. The solar apogee is fixed at Gemini 5.5 degrees. With the refined method of the seasons, they found out that the solar apogee indeed moves. It moves at the same rate as precession. Hence, now they have a better eccentricity, they have a new value for the solar apogee, and these are fundamental. I'm sure I hope there are astronomers here. These are fundamental values to any kind of astronomy that you want to do. These are the basic building blocks. You build an astronomical theory on the basis of inclination of the ecliptic, solar apogee positions, rate of precession. All of those fundamentals are built into it. So now, in one shot, by just shifting the method of observation, you get a new eccentricity, you get a new solar apogee over there, and of course, now that you have the position of the solar apogee, which is right in here now you can begin to say, if I am an observer here at the Earth, the sun will move at uniform speed with respect to its own circle, which is away by a new eccentricity that they just determined, and now I can calculate from the mean motion and the eccentricity, the true value for lambda for every day of the year as the sun is moving. Because the true value of lambda is nothing but the mean value plus or minus the equation. But the equation itself now, since we have a new eccentricity, is a different equation, because C is different from that of Ptolemy. So you have a new eccentricity, a new solar equation, a new lambda, a new solar apogee, and the new inclination of the ecliptic, all of those fundamental building blocks, while you are still trying to determine when shall I pray at noon. See, a simple religious requirement says pray when your shadow is that long. Jesus, already you find out that this is too much involved mathematics, and I hope it is impressed upon you, but quickly we will move it. So when you take them all together, by just this simple requirement, and you find that you have to find a new inclination, which we just found, the solar apogee, which we found it to be at the same rate of precession, which was also to be found erroneous in Ptolemy, because Ptolemy says the precession moves at the rate of 1 degree every 100 years, hence the origin, and I see there are enough older faces in the audience here to remember the famous song from the musical Here. Here is the age of Aquarius, or there comes the age of Aquarius. It was based on that precession of that. They turned out that the precession of 1 degree 100 years is too slow. In fact, precession is 1 degree every 70 years because they have new ways of measurement now. And it is still the better value. The 1 degree to 70 years is the value that we still use. And the new eccentricity, new solar equation. If you were an observer or an astronomer living in Baghdad, inheriting the Greek astronomy with all of those values erroneous, what would you say? And you're a good astronomer, meaning a good scientist. Shall you believe everything? Or you begin to say, well, maybe this material, we should rethink it. And what they did, they indeed rethought it, they recomputed, and now they began to produce what looks like computer table for you. When computer outputs, by the way, used to come from those flops that fell like this, felt like accordions and all of that. You had these kinds of things, and here you see, they tabulated everything so that you don't have to solve the problem every time you need it. They'll give you the number, you read it out of this, and here you see the height at noon, the beginning of the afternoon prayer, the end of the afternoon prayer, the dawn prayer, the twilight prayer, and they give you the shadows in the lengths of feet and so on. So in other words, this gets regularized and solved for any locality that you can think of, except the places where there is no civilization beyond 44 parallels. They marked it even on instruments. So when you get those astrolabes, we'll see some of those astrolabes, you see this curve here is called Salat al-Dhuhr, the beginning, the prayer of the, Salat al-Dhuhr. That is the Zawal, that is the high noon. That is after the noon. That is the beginning of the afternoon prayer. That is the end of the afternoon prayer. Those are marked on these astrolabes so that you will also, you don't need to go and compute, you don't need to read tables. All you have to do is you look on your astrolabe and you'll be able to perform the prayer. So in other words, they solve the problem, they carry it to the logical conclusion, and then at the very time they make it simple by creating a machine for you. They created technology to be able to answer that problem. Now, the second problem, if it were only, if Islam had said, pray 5 times a day, it would have been so easy, we would have solved it and finished with it. But no, it didn't stop at that. It made another requirement. It said you have to pray in the direction of Mecca. Where is Mecca? For us right in here, if I ask you where is New York, don't tell me it's 95 south. I know it is 95 south. But where is it from this room? Is it this direction, that direction, that direction? So directions on a sphere are not trivial. So when you tell somebody that, and actually there is a Quranic statement here that simply says wherever you are, you have to turn your face in the direction of the holy sanctuary, which is down in Mecca. Every time you pray, you have to do that. Meaning, you have to solve a problem of the following nature. If this is Mecca, you are here in New York, you have now to solve these spherical trigonometric problems in order to determine in which direction from New York you need to look in order to face Mecca. Breaking it down a little bit, it means that you have to calculate on your local horizon the length of this arc, which is from your south to the point where your meridian hits Mecca. That is your zenith here in New York, you pass this arc through Mecca. So this is your local arc that is measured, again dependent on the solution of this problem, of this triangle, of which this angle Q is to be determined. Break this one separately, and then you can see the kind of mathematics you have to do to determine where is that angle. You see the use. The sine law is in here, the cosine law was used before. All of those values of multiplying sines by cosines, cosine squares, dividing them, this is not a trivial problem, including our use of modern computers. I give my students an assignment and say, compute the direction of Mecca from your apartment here in New York and come to me with the solution. And no two students get the same, even though they are using it. But again, now I know why, because there are no two Windows machines that work the same. No two Windows ever respond the same way. But the problem is considerably sophisticated, because at the very end, you are solving a problem of this magnitude. This is not trivial, and this was done already in Baghdad, again, between Baghdad and Samarra, in one of those cities, was already done in the 9th century. In other words, the whole idea of spherical trigonometry. I know the Greeks had the Menelaus theorem, and they could use that theorem to solve all sorts of problems. But the facility of using the sines, the cosines, as you see, the tangents, the cotangents to solve these problems, that was only developed during the Islamic civilization. So you have a whole new field now of trigonometry, of spherical trigonometry, being developed specifically to answer the question of when to pray and what direction to pray. And of course, when you finish all of that, you tabulate all your results. And my colleague David King, using the Yale computers way back in the 70s, double-checked as the direction of Mecca from all those cities that are tabulated here. And look, he found the maximum variation of an error is less than 20 minutes. That is not trivial. To do all of this, again, to remind you, imagine you are solving this problem and you are getting it right as well as a good computer can do within 20 minutes of arc. That is damn precision that I think it will make any mathematician just blush. Habash al-Hasab in Samarra continued from there on. As I said, these are the trigonometric functions he plays with, these are the definitions, and I just put his slide here just as a tribute to Habash al-Hasab because very few people know his name, the poor guy. They went the second step. On the back of astrolabes, this side of the astrolabe is nothing but the sine functions of an angle, the cosine function of that angle. So now you have your trigonometric tables are on your little machine that you carry this machine in the astrolabe. Also on this side in here you are measuring the tangents, on this one are the cotangents, and on this one these curves here that end with Baghdad, for example, that will give you the direction of Mecca for the city of Baghdad, city of Shiraz. And you see they mark them, and that will give you also the height of the sun at noon for all of those latitudes that are marked over there. So the mathematical solutions are also simplified by turning them into little technologies that you will be able to see them. So all of this was not even dreamt of in Greek science because there was no need to pray 5 times a day. You can pray as much as you want in Greek, and you don't even need to face Mecca, you face Athens, and Athens is always in sight. So why would you... So now all I want to impress upon you is that the simple requirement that we think is such an innocent requirement generated all of this mathematics. All of these disciplines were as a result. And they did further than that. They even developed mapping methods so that you have now a map for the directions of every city. When you put this arc, this one tells you the direction of these cities from Mecca, as well as it tells you also the distance of the city from Mecca. Because as a Muslim, you are supposed to visit Mecca at least once in a lifetime. So now you can tell how long you have to travel before you. So not only you know the direction, you can know the measurements. All of these are also neatly projected in this map as we see it here. Now let us see. As I said, these are only 2 examples, by the way. I wish I had enough, like a whole semester. We can plow all of those examples, and you can see how religious requirements were generating very, very sophisticated mathematics and sophisticated astronomy, mathematical geography in all of those directions. But this was happening also in other disciplines. For example, Islamic civilization also brought the so-called Indian numerals that you call them Arabic numerals. In the Islamic world, they call them Indian numerals. They know where they came from. But it was through the Islamic civilization that these numerals have become universal numerals. If Europe was left on its own, we would still have to be playing with numbers like this. And I would like to give the students a homework. You try to tell me what is the value for this one. Okay? I would also ask the scientists here, when you go to your lab to record the data that you get from your lab, do you use this system or you use this system? Okay? So just the simple things that we take them for granted, they are also part of that production of the numerals themselves, by the way. For those who don't know, Arabic reads from right to left. And that's how they appeared in the original Arabic manuscripts. And this man is telling us when you come to the numerals, you can write them in one of 2 ways. 1, 2, 3, 4, 5, 6, 7, and 9. And then otherwise you can have this other alternative. You see number 3, we recognize it. 4, 5, 6, you can recognize that. 7, 8, and 9. And then he says, when you finish this, you add a little 0, you come to the tens. When you finish with the tens, you add 2 zeros, you come to the hundreds. And that's how these things operate. So he's teaching us how to do little arithmetic. The earliest that I know of an English treatise, of course, that you know English goes from left to right and all that, and until it hits the numerals. They go 1, 2, 3 from right to left. What does that mean to you? It means the person who was playing with these numbers had not yet digested their full significance, and he or she thinks that the order in which they are written has something to do with it. So there is a mystery in the order. And hence in the English treatise we see in that way. The French, who are not very much more intelligent, they had, but they created columns that the New York Times can use. This manuscript has 2 columns, you see? And again, it goes from left to right. When he reached the numerals, look what he does. He jumps down one line, writes 1, 2, 3, 4, goes back and writes 5, 6, 7, 8, 9. Because he still thinks that the order from right to left is extremely important. It took 200 years. This manuscript is 1275. 1475, they could write them from left to right, and they felt it's okay. That simply means that cultures take time. We have not yet gotten over the old Babylonian concept that every 60 seconds make a minute, every 60 minutes make an hour. We are still using sexagesimal system that was invented in Babylonia, but for every other measurement, we use the decimal. Or we use that funny system that's called inches and feet and all so on, that nobody knows how it works. Now, the fact that every time you balance your checkbook at the end of every month, you're still doing Arabic mathematics. You arrange the units, the tens to the left, the hundreds to the left, the thousands. In other words, from right to left, you put the ascending powers of 10. Nobody, any mathematician here, and I did it for exercise, any mathematician can tell you can arrange them in the sense of the language, from left to right, and you still get 7,113. Why don't we do that? Because we are stuck. We are stuck in the same place that Arabic manuscripts left us in the medieval times. And we still play with them, and they are still part of our daily culture up till today. They also, in the 10th century, we have the earliest manuscript in which not only that numbers were developed beyond their order, and they knew how to arrange them and all that, that they knew that the so-called old fractions that the Greeks did not treat as numbers. The value 3 over 5, for example, in a Greek tradition, is the ratio between 2 magnitudes. It's not number. It is a magnitude of length line 3 over a line of length 5. And hence they deal with them as proportions of magnitudes, and they don't treat them like numbers. But in 952, when this manuscript was written in Damascus, not only did this guy treat the fractions as numbers, he also invents, you see this little slant over here, that is the decimal point. He says you can treat them like decimal, like numbers now, and hence you can multiply them, divide them, do all. Imagine if we had to break out all our computations in one value, and then a number like 3.25 multiplied by 6.7 becomes impossible, because we have to break it into magnitudes, into numbers, and then recombine them if we were to do it the Greek style. Then there is this discipline called algebra. To start with, there is no Greek word for algebra. Algebra is an invented Arabic word. It was invented specifically to answer those problems that are listed here at the bottom by a man called Al-Khwarizmi. He says he has written a book called Hisab al-Jabr wal-Muqabala in order to solve these kinds of problems. Needs for inheritance, will, settlements, obligations, commerce, and so on and so forth. What is he doing? I don't think I have too much time, but I'm going to quickly tell you what is the difference. He says there is a difference in strategy. When I give you $100 and I say, take 1/10 of this $100, give it to the charity. Take 1/20 of it, give it to your school. And what is the remainder? You easily divide by 10. You are playing with known quantities. He said there are times when we don't know what is the value. We are told that somebody died and he left an inheritance. We don't know what's the inheritance. But we know 1/10 went to charity, 1/20 went to school, and what was left was only $5 at the end. What's the original value? He said, in this case, we have to assume the original value is a black box. is an unknown quantity. And we have to operate on that unknown quantity by taking 1/10 of it, meaning treat it in abstract. That's extremely important. To take an unknown quantity and be able to divide it by 10, divide it by 20, add it, subtract it at the end, force that unknown quantity by saying x equals so and so. The idea of forcing in Arabic is jabara, literally to compel. And hence the discipline is called the discipline in which unknown values are compelled to have values. So Khwarizmi did not have a Greek word for it, so he invented the new Arabic word, inserted it, and that became his book on algebra and al-muqabala, and I hope I have the translation for it, which I don't have it here, but the same person who gave us this algebra is al-Khwarizmi, and his also name became our algorithm. This book, Al-Algebra, here becomes our term algebra, which are things that I think still used up till today. Let me talk a little bit on planetary theories before I run out of time. And that is a new concept that I hope I will be able to convey it without too much difficulty. The Greek tradition also assumed that every single motion that we have, there has to be a sphere that is responsible for that motion. Motion doesn't happen just on its own. Bodies don't swim like fish in the water. There is something that moves them. All the planets, and that's what Aristotle says, and if you read the Greek tradition, except that it has a problem of the following. Because we have a daily motion, meaning every day we see the sun come up and we see it shut down, together with the whole universe. All the fixed stars come up and do. But then we also know that the fixed stars precess backwards by 1 degree every 70 years, or according to the Greeks, 1 degree every 100. So each one of those two motions, a sphere has to be responsible for them. And the Greeks assumed that those spheres are concentric. They are both with the Earth in the center. Well, this may make sense, except that the outer sphere that moves everything inside it once every 24 hours could not possibly move this sphere together with it unless if there is some friction between the two spheres. And since both spheres, according to Aristotle, are made of an element called ether, which is not of the same as the other elements like earth, water, fire, and air, ether does not partake in that, therefore it is impossible for this sphere to move the other. And in the 9th century, Muhammad ibn Musa says, here, I'm sorry I don't have the translation, but I'll quickly tell you, it has become clear that there is no possible arrangements that can have those two spheres and hence cosmologically work the way the Greek text expected to work. So we have a critique of the Greek text coming in as soon as they get translated into Arabic. They also began to look at the Greek text and they began to find mistakes in the original Greek. And here I cite for you the length of the lunar month as it is in the Greek text of Ptolemy, where Ptolemy instructs us, by the way. He says if you take this number of days plus 1 hour, divided by so many times of the moon lunar cycle around the earth, meaning of so many lunar months, you will get the exact lunar month, and he gives it to this 29 days, 31 over 60. Here again, you see, the sexagesimal system of the Babylonians is built in. 50 over 60 squared, 80 over 6, and 20 over 6 to the 4. The translator by the name of Al-Hajjaj here, who translated this text from Greek into Arabic in 829, says, I divided those two numbers. The value is different. And he gives us here 29, 31, 50, 8, but then there is 9 before you get to the 20. So those people were not just translating, they were double-checking the values in the Greek text. And now they're saying this text is untrustworthy. If it is a simple division and it doesn't get it right, so how can I trust the other things? Then they begin to find that there are other problems, and they began to write genre of literature that is simply called doubts against. This text, for example, is doubts against the famous physician Galen. So because Razi has found many, many problems with the medical text, so he devotes a special book. He says, it is Doubts Against Galen. The second one is Ibn al-Haytham, the famous Alhazen of the Latin West, father of optics. He also writes a book here that he calls Dubitationi in Ptolemaium. That's because Sabra wants to say that Latin is good. But it simply says it is doubts against Ptolemy. Of the doubts are that some that we will see, but the most important doubt that I want to focus on it a little bit is the doubt that in Greek astronomy, Ptolemy tells us that if we are at the Earth, the planet will move on an epicycle, which itself, the whole epicycle, is carried in this shell of the blue sphere by a motion of the blue sphere itself that has to move in place, but not on an axis that goes through its center, nor on an axis that goes through the Earth, but on an off-centric axis that is called the equant. That is as physically impossible as finding a black swan, I think, as my friend down there. And let me tell you how impossible it is. Any basketball player will tell you that for this spinning to work, the finger here has to be on an axis that goes through the center. The minute you move it, the whole universe will collapse. They didn't have the basketball, but they had the intuition that it is physically impossible to assume this kind of configuration. So they began to say, maybe we should invent a whole new astronomy. One of them is that also that the moon, the movement of the moon, according to Ptolemy, that is to the Greek text, if we are placed here at the center, he tells us that the moon, the center of its epicycle, will move along these red dots that you see them here, because he needed, for observational reasons, he needed to account for a large angle that takes place when the moon is at quadrature. What Ptolemy forgot to do is that, and the way he solved it, he said, one way of accounting for a large angle is you bring the body closer to us, which is a nice phenomenon that distinguishes between the size of an object in reality and the size that we see. And the example I always give to the students is that when I put my hand in front of my eye, it covers the whole wall. It doesn't mean that my hand is bigger than the wall. It simply means that my hand is too close. And what Ptolemy did, he says, okay, I can account for the large angle by bringing the whole mechanism closer to the Earth. He forgot to notice that bringing it down to 39 units from a distance that was 60 units is almost halfway down, which means that if it is brought halfway down, then the size of the moon at quadrature will have to be twice as big as it is when it is a full moon. And Ibn Shatir of Damascus says, وَلَمْ يُرَ كَذَلِكَ. I have never seen the moon at quadrature look twice as big as when it is a full moon. Hence, I need to create new mathematics to solve it. And Ibn Shatir says we can do that. We can account for a size, larger angle, but we keep it at the same distance so that the size of the moon will not be different from it is here or it is there. So you see, this new mathematics of having to concoct one epicycle on top of another epicycle solve the problem and preserve the observations, and the size of the moon remained the same. This solution became so attractive. Ibn Shatir died in 1375, as you see here. The solution became so attractive that it got picked up by Copernicus in 1543, about 200 years later. You see, it's exactly the same arrangement. Arrangement for arrangement, cycle for cycle, arc for arc, and so on. So you're entitled to say, since Copernicus is not following the Greek model that we see it up there, he is a Renaissance man, and yet he is not recapturing Greco-Latin antiquity. Instead, he's recapturing Damascene latest research. So you're entitled to say, did he know about the works of Ibn Shatir? Or is it just coincidental? And these coincidences do take place, except that he didn't only take that from Ibn Shatir. He took another theorem from a man called Nasiruddin Tusi. This is the proof of the theorem in Arabic. Well, what does the theorem do, I think, is simple. I can show you exactly what is the function of this theorem. It creates linear motion as a result of circular motion. You see this red, this red point oscillates up and down as a result of the outer sphere moving this direction, the inner sphere moving the other direction. So he needed it for all sorts of other problems. I don't need to go into them. But that theorem was created by Nasiruddin Tusi in 1247, articulated in full text in 1259, it gets used by Copernicus in 1543. But Willy Hartner, the late Willy Hartner of Germany, noticed something more interesting. He said, look, where the Arabic has alif, the Latin has A. Arabic has ba, the Latin has B. Arabic has jim, the Latin has G. The Arabic has dal, the Latin has D. Arabic has ha, the Latin has H. Wait a minute. If I ask you to draw on the board a triangle ABC, you put ABC wherever you want. Why are they being put in exactly the same places where they were in the Arabic text? Except that one guy from Harvard objected. He said, see, the Arabic has Zain, the Latin has F, so therefore he was not copying all the way through. I say, yeah, but you haven't looked at Arabic manuscripts. Zain and Fa in Arabic, this is a Zain in Arabic, this is a Fa in Arabic, this is a Zain, this is, see how similar they are? So obviously somebody misread the Zain as a Fa. As simple as that. Otherwise the model was being, or the geometry of the model was taken wholesale. The next step is the movement for the planet Mercury. And that one, this is how it appears in Ptolemy, and you see that it was not sufficient. Ibn Shatir creates a new model. Here, instead of the spheres, I just represent them by their radii. This is the one in Copernicus which renders exactly the same radius to radius, the same connections as they are there. And at the end, also Copernicus says for point P, he says, I need to build those two spheres that we talked about so that we create linear motion out of that. And these are the two spheres that are already in Ibn Shatir's work. But when Copernicus takes the whole work of Ibn Shatir, now this is the work of Ptolemy, this is Ibn Shatir, the whole model gets carried away and gets brought into Copernicus with the following very important thing. Remember what I told you, the size of an object depends on the actual size and the distance of the object. I think Copernicus got confused when he saw this orbit of Mercury, resulting orbit, at quadrature, looking bigger than this one. He forgot to notice that the center of the smaller one is closer to the Earth, and therefore the blue angle is still bigger than the red angle, despite the fact that the circle that is associated with the red is in absolute value larger. So he takes the model and tries to describe it, and that is the description that he gives. He says here that the planet at quadrature has the largest circumference in here, but that's how it appears, which is the trick. In other words, for an observer on the Earth, he claims that it appears to be the largest when it is here. Sverdlov, who translated the work of Copernicus, says, no, Copernicus does not realize that the model has to produce the largest when it is at 120 degrees, not it is at 90 degrees. And then concludes, Sverdlov concludes that he says this misunderstanding must mean that Copernicus did not know the relation of the model to Mercury's apparent motion. Thus, it could hardly be his own. In simple words, he is saying Copernicus got a model that he doesn't understand yet how it works. In the same way the numerals, you see, he still has not digested it yet. And the description that he gives for it is an erroneous description. Therefore, Sverdlov says, since it is Ibn Shatir's model, this is further evidence, and perhaps the best evidence, that Copernicus was in fact copying without full understanding from some earlier source that we don't know. That's the last of it, and I think I'm almost within 3 minutes that I can summarize. What you have seen, I hope, convinces you that Arabic Islamic science did not preserve Greek science. It obviously reshuffled the whole thing, recreated new astronomy, it created new algebra, it created new trigonometry, it created new planetary theories, all of this. Two, that because of this activity of recreating, because of this updating of a better science, and the values of this better science are still with us, as we just said, the inclination of the Earth's axis is still with us. The inclination of the ecliptic is still with us. The rate of precession is still with us. Because of these better values, that's why this science was useful to the Renaissance intelligent astronomers like Copernicus. He went and got them because he wanted the latest in science. And I say, for all due respect to Copernicus, we will actually be unfair to think that he was just another Renaissance man. He was seeking knowledge from Greco-Latin antiquity. A scientist would not do that. A scientist will reach for the latest in science, not for a science that was then 1,500 years old. And hence, we should pay right tribute to Copernicus for being able to locate where is the best science and to be able to deploy it and then take the next step and make it heliocentric. That is the way to assess Copernicus. Therefore, when we talk about Islamic science transforming Greek science, this lesson, I hope, is to be learned by people who study Western science so that we can assess Copernicus properly, that we can assess the physicians properly, who also took all sorts of medicine. If I had time, I could explain it to you. And who took all of the latest science, the mathematicians who took algebra properly, who took all of these terms as they were created 150 years earlier in Islamic civilization. Thank you so much, and I think I can stop at that. Yes, let us be in the light of day. Yes.
Questions? I was wondering about the division in the Islamic world in the 8th, 9th, 10th, 11th centuries.
Yeah.
When you have Damascus as one center and Cordoba as the other.
Yes.
Was there a similar, was there any creation of science, Islamic science in Cordoba?
Yes.
Was it simply transported to
No.
Islamic culture?
Yes, I'm glad that you brought this up because, as indeed, in May, I'm going to give a talk in Alexandria at the new library, the Alexandrina, Biblioteca Alexandrina, on forgotten manuscripts. And one of the forgotten manuscripts that I will talk about is a manuscript that comes from Toledo. And the reason I know it comes from Toledo, unfortunately, the first page of the manuscript is missing. Okay, so we don't know who wrote it. But from the text inside, the author says, this result was reported to me by my friend, Zarqiel, who worked on Toledo. Zarqiel, we know him from all sorts of other places. He lived about the year 1050, 1060. So he was producing, and this text is produced here. In the same text, which of all places, by the way, I found it in Hyderabad, India. Unique copy. We don't have another copy of it anywhere in the world, neither in Toledo, nor in Spain, nor anywhere else in the European library. In it, he says, this is the same text, he says, I got this result from Zarqiel. But the critical part where it varies from Greek astronomy, I wrote it in a separate book, which I called it Recapitulation on Ptolemaic Theory. That book, I'm looking for it. I'm looking for several others, but in Alexandria, I will talk specifically about this one as part of the forgotten books. We don't know where they are. We hope that at one point it will surface. Now, in terms of operational mathematics, I have to say that the material that began to actually create most sophisticated critiques of Greek astronomy and create alternatives to Greek astronomy, unfortunately, did not begin to take place in the Islamic world until after the 13th century, which is a time, by the way, when everybody thinks that Islamic civilization, Islamic science went to sleep, which is obviously erroneous because people don't read text. After the 13th century, by this time, Al-Andalus was experiencing the Reconquista. So you really do not get a lot of activity happening at that time at a high scale. They were literally on the run. And that run ends by 1492. As you know, no Muslim, no Jew was allowed to remain in that place. They all had to go outside the world of tolerance. Remember how tolerant it was? Yes, sir.
It's sometimes said that the Greek astronomers didn't think of their models as reflecting physical reality,
Yes.
but
Yes.
it was more a mathematical device.
That
I'm
is-
wondering if the Islamic astronomers thought
Absolutely.
they were really describing the physical world.
Brilliant. And I think the person who started that rumor that the Greek astronomers did not think of their models as physical realities is Pierre Duhem. And Pierre Duhem in the 19th century, beginning of the 20th century, was very embarrassed by that spinning ball as being a reality. So he says Ptolemy could not have bypassed that absurdity. Unfortunately, Pierre Duhem does not tell you that the text of the Almagest was followed by another text, which is called the text of the planetary hypotheses, by the very same Ptolemy, in which all of those spheres are represented in physical spheres. So no astronomer No astronomer before Newton would ever think of things moving in space at their own will. They were all moved by specific spheres, arranged in specific ways. The challenge for the mathematician is to account for all the variations that you see, the retrogrades and all of these things, to account for them within a system of spheres moving on their axis. And the attempt of all of those Muslim astronomers was indeed to do that. And Copernicus follows this in exactly the same steps. Of course, he violates the cosmology by shifting it to the sun. That I don't know. Why does Copernicus do that? You see? But there is no doubt in anybody's mind that Ptolemy was thinking of physical spheres. And he does say so even in the Almagest, in book 13 of the Almagest, where he's speaking of inserting little circles to account for the wobbling in latitude. He says, let people not accuse me of doing things perfectly, but who am I, the human, to imitate the action of the divine? Meaning he has no solution for it. But he was polite. Yes, ma'am, in the very...
I have a question. I was really curious when you...
My ear doctor says for women you have to ask them to speak louder. Yes.
I'm wondering about the birth of that genre, Doubts Against.
Yes.
And if that genre existed in Greek time, and if it persisted afterwards, because of course that's
Yes.
very common nowadays in critiques and reviews and papers
Yes.
and processes.
Yes, on both counts. Actually, there are critiques, aporias are called in the Greek tradition. There are people doubting earlier people, but nobody has devoted a full book to a specific author. In other words, in the sense that we saw Razi devoting a book to critique Galen, Alhazen devoting a full book to critique Ptolemy, the unknown astronomer from Andalus recapitulating Ptolemy. This genre, and then also not only that, in the Greek tradition we have some opposition, some rejection, some doubts and so on, but none of them were ever taken as a program to produce better mathematics or better astronomy. The Arabic tradition, Ibn al-Haytham's challenge began to be the starting point for all the later of Ibn Shatir, Mu'ayyaddin al-Ardi, Tusi, a whole series of astronomers. They say, if there is this doubt, we can fix it. There is this problem, we can fix it. To such an extent that I get an astronomer in the 16th century, he died 1550, from the city of Shiraz in Iran, who writes a book, which I am editing right now. I'm in the process of editing this book, which he calls, listen to this title, a beautiful title. He says, the solution of all the insoluble problems that were mentioned before. Hal ma la yanhal. Literally, hal, for those who know Arabic, hal ma la yanhal. The solution of all things that could not be solved. Let me show you how much mathematics we can do. And he actually says, not only that Mercury can move in this fashion, this other mathematics can produce this motion, this other, he goes for 5 different ways of describing the motion of Mercury to tell you that mathematics itself does not have a truth by itself. That mathematics is a language of describing motion, and hence, as a language, I can use this mathematics, this mathematics, this mathematics, this mathematics, in the same sense as if I can describe the motion in French, in English, in Spanish, in Latin. You see? So they reach that sophistication, which is unparalleled. There is nothing like that in the Greek tradition that I know of, unless somebody springs up something on me that I haven't seen, which I doubt it very much. Yes, sir. We met before.
And we'll meet again.
Okay. No, I want to say the face is very familiar. So.
Fascinating. Well, I'm wondering if you could give a brief sketch of the educational world that must have
Yes.
underlain this.
I'm going to be very crude. I'm going to be very crude, and I tell you, my sketch is not going to be very good for students here. The most destructive education system is schools. Why?
We know that in hand.
No, but I have a good reason for that. Because it tries to bring everybody to the same lowest common denominator that we assign in the curriculum. But I was happy to know, by the way, that this college is experimental, in the sense that it allows people to design their own speed and their own ways of doing things. That is a step in the right direction. In the medieval times, all this sophisticated thing was done by tutoring, by individual tutoring. And this is not good for the students to hear. If you were to study with me this thing, you will come and service me in my house, i.e. you work as little slaves, you clean around the house, you do all of these things. And then in the evening, you will be very lucky that we will sit together and I will read my book to you. And when you finish that book, I will sign that book and I will say, a student by this name at this time read this book with me and I discussed it with him or her and I certify that this student can now teach my book. That is called licence, certificate. That is the equivalent of your BA. You don't get a BA in everything and become knowledgeable in everything. We know you don't. You get only a certificate to teach a particular book that you studied with a particular professor and got certified. That allowed the student and the teacher to go at any speed that they want, depending on the intellectual gifts of the student. That is the best system of education, and I think they did it. Now, of course, the next question is when did it stop, but that we will answer it in the next book. Yes, sir, at the very back.
So what happened to what happened to sort of reverse this tradition or to stop it?
Didn't I tell you we have another book coming? It's this one. Yes, what happened is many problems that I don't have the time to tell you about them now. But let me tell you something. Most people begin to look for this, and some of them live in the woods around this area, to begin to say, Islam did not have the right scriptoriums in the right clergy or did not have the same law to do this other law and all of that, and they forgot that the whole world did not have. In other words, the peculiar phenomena that has to be explained is why did Europe take off in the 16th century and all other civilizations began to look like they declined after the 16th century, not before. All those who fixed the statistics or fixed the evidence to say that it began to decline after Ghazali wrote his famous critique of philosophers in the 11th century. After that, science had to die. All of this science that you saw was written after the Ghazali, after the 13th century, well into the 16th. But indeed, after the 16th century, the whole world went into decline in comparison to the logarithmic ascension of the production of science in Europe. That is the subject of my next book. If you know of a funding agency that will give me 3 years, I need 3 years to finish writing it, okay? That's the only way. I have to beg. What can I do? Okay, I think we killed them.
Thank you very
Yeah.
much.
Thank you. Okay.